All right, so we're going to start the first session. With each speaker, please giving a short summary of what you have put online, take about 10 minutes. And afterwards, we're going to have a panel discussions with questions from us and the auditorium, as well as we consider the chat. So our first speaker was Ryad. The floor is yours.
Should I share my screen? Okay, let me. So
yes.
If I understand correctly, you just go through the slides, right?
Maybe make a summary.
Yeah, of course.
Okay, so yeah, okay, sounds good.
Okay, so I'll do it in a nutshell, 10, 11. Okay, thank you so much for organizing this and for inviting me. And so the talk I gave was something called What Happened Over the Last 10 Years. And for those who just joined the community, where we came from, where we are, what's out there, and what are the challenges to, I believe, will take us to the next step. So as I mentioned, we are here today because almost 30 years ago, neuromorphs met on a mountain in Telluride, and their scope was to develop new sorts of hardware, new sorts of computation, and go beyond what people know of hardware and architectures. There's a nice book about it called The Silicon Eye that Toby once gave me, I think 12 years ago, I don't know, a long time ago. I still have it. And it's a beautiful story about how neuromorphic streams started. And when Carver was a young professor, and of course the biggest achievement back in the days was Misha's camera that makes the cover of Scientific American. So although we are in an engineering space, I think what these guys, at least the people who started this field, were doing is really to understand and bring what we do today as engineering as a basic science, which is, you look at something, you don't understand it. In our case, it's perception. And so you try to follow the normal lead of basic science, which is you observe, you try to understand, come up with math models, and then the applications are huge, because if you look at the stars and you make statistics, that doesn't give you lots of understanding apart seeing that moon will appear there, the stars there. But if you understand the orbits and everything, well, you can go to much more fundamental things. It's a deeper understanding that opens path for other things. So honestly, I know most of us are engineers, but we have a unique chance here to make computer vision as a basic science, because from one side, it's exactly the same scheme. We have eyes and brains. You can record from it, try to understand it, model it, and then build things, which can be a camera in our case, or processors. And then the applications are huge, because if we change computation, well, we can change almost all our society, from networks, machine learning, autonomous driving, everything, BMI, looping back. So I honestly have always thought of neuromorphic that way. It's a unique chance for us not to go, just to hold a line, which is my work conforming with the data? If so, it must be not that wrong. So why cameras? It's because retinas are what people believe the most approachable part of the brain. It has always been an exciting space for people to try to understand the brain. It's a 7-layer structure. It's very easy to record. This is, I think, my setup in Paris before I left. I mean, setup we share, and so it's very easy to record from eyes. So event cameras, it's a long story. I think started around 2000 after Misha's. There's been lots of work before. So there have been many attempts. And the one that reached us, I think, originates from Jörg Kramer's idea of differential signaling that has been then taken by Patrick Lichtsteiner, Toby, and Christoph to do the DVS, and then the extension of the DVS, which is the ARTIS, and everything that followed. And you see, it's really an incremental effort. And today, if we are here, it's because somehow the field made it, and cameras are becoming a commodity. I think you can buy cameras from all over the place. When I started, I mean, 15 years ago, there were only one place and then two places, and no commercial of any sort. So why is this a great chance for us? First of all, as I said, it's because somehow it mimics what the brain is doing. So you can read neuroscience and get insights of what you should do. And then the space is wonderful because you see when you, at least in the current thread of event vision, is every dot you see here is an event. This is times 0. Everything is new, you get the frame, and then every dot comes with X, Y, a very nice temporal precision T, and the gray level. And so when you see that, the main idea of, I would say, the historical path of neuromorphic was to use this timing of these events and try to combine some computation between space and time. And the other advantage of these sensors is the really low bandwidth and low output. It's not really true with the last sensors because last sensors are blowing really lots of giga events per second, even with compression. But you see here, this is a QVGA mounted on the car, and you have around 100 events per millisecond or 10th of millisecond. Sometimes it rockets, you have 800 events, but it's still much less data than this baseline here that is a camera seeing at 30 frames per second. So you see that the advantage of these sensors is really to try to find a way to process these events and never allocate memory to store everything, to go back to any sorts of frame. Maybe you can, but I think all of you know what I think of frames, but you'll see I've milded my position here lately. And here you see something really nice. It's a hand waving. You see when you, in blue, it's the number of events just to show you what's happening. And you see the hand waves, the temporal resolution is so high that you see it slow it down and then accelerate again. And what really matters is here, what I put in red, which is if you were to allocate any type of deep network, a deep temporal AI network, and you would allocate all the planes and you make them work, you would see that your planes will be, for every database we use, 8% occupancy, 3%, 1%, 1%. So 99% of those planes are empty. And it's again another way, not only are you losing the advantages, but you also lose lots of resources. Yeah, so frames, why are they bad? All of us know that when you have a robot, you'd like to go as fast as possible, but then you will have oversampling, meaning you get information that are useless, like this background here, whereas what you're really interested in is the movement. And so if you increase the frame rate to get the movement, you will increase all the junk information you already have. And if you reduce it, you will not, you will reduce that static part, but you will miss the dynamic part. So it's really a paradox. You cannot go. You have to find something in between according to the powers of computation you have. And it's unfortunately very high power and high latency because you just have to take all the information out and throw most of it. So just for those who don't know, we are using images today as a history momentum that comes from this invention that it's called the camera obscura, the black room. It's a pinhole model, and it could have been lost in history, but what happened is that painters start using it to paint faster and make more money and move this box from castle to castle. And over the years, this guy has been replaced by pixels and this very sloppy and brittle optics by nicer, cheaper plastic optics. And that's it. That's why we use frames. And that's why even 300 years ago, 400 years ago, we just kept doing this. So today,
sorry, could you please keep it to 10 minutes?
Am I not 10 minutes? I have started at 11, 2 minutes and I wrap up, okay? Thanks, Cornelia, for the reminder. So the event computation today, I think, is split in two waves. People who advocate for incremental. Incremental means one event, one update. And it makes sense when you see what I just shown you that this is the way I believe to go because it's very low. But the other side is really to try to stick somehow to our past, which is frames, and generate images, do batches. And the main reason is we have the hardware. So to make it very short, I think the main problem we are facing today is linked to the arbiters. Maybe we can talk about it. I think Kobena has given a full talk just on arbiters. So the arbiter we use is very old. There's a hack found by Cohen, I think around 2001, that nobody ever challenged. It's this idea that if you want to compute with time and you want to take the information out of the pixels, a pixel must ask a request on the y-axis, on the x-axis, and if it's both acknowledged, goes out. And that's very costly. And most of the arbiters try to maximize their position, meaning if they took a pixel out here, they will tend to try to stay here and not go elsewhere where there is an event, and that scrambles time, and that creates lots of confusion. So this is really, really bad. I happen to work with few sensors that don't do that, and it's really night and day. And the other big missing thing that we have to sort out is we need a good piece of hardware that allows us to write our equations to make use of the event-based. And currently the threat is to replicate what nature does. I think we've all done some sorts of Lohi or True North or whatever in our labs. And we know that today it's very limited cases. We don't know enough of the brain. I think that's it. The rest can be discussed when we are all together.
Oh, thank you very much.
You're welcome.
Okay, so our next summary would be then by Greg Cohen, who will tell us about applications from the University of Western Sydney.
Thank you. Can I just share my screen quickly? That should work. All right. Hello, everyone. I'm Greg Cohen from Western Sydney University, from the International Centre for Neuromorphic Systems. And yeah, apologies if it's a bit later for us here. It's after midnight, so forgive me if I go a bit slow, if I mumble more than I normally do. So I'm going to talk to you today about a few things, a bit of a range of things, starting from some space tracking applications and going all the way to some of the more interesting and perhaps more fun type things we do, which is really building robotic foosball tables and robotic pinball machines. And I'll explain to you how we're doing that and why there's some science behind those tasks that we're doing. And I think the reason that we're doing this is that, and this is sort of core to what we do at ICNS, which is really start with an application, with a problem, and then try to work back from that and say, how do we solve the problem with neuromorphic sensors or processors, and then the algorithms that tie them all together. And it's really nice to have a well-defined problem because it makes the rest of the system so much easier. You know, you can actually optimize everything when you know exactly the task you're trying to do. And I'll show you why that gives you some really big benefits. And by just changing the sensor, you can do things you can't do with conventional sensors. And we've leveraged that, for example, and primarily in this field of space situational awareness, or as it's becoming called space domain awareness. And what that really is, it's really tracking objects in orbit around Earth and now in orbits around the moon as well. So primarily satellites, but a lot of space junk as well, because we've really been pretty bad about cleaning up after ourselves in space. And there's an enormous amount of debris in orbit around Earth, as well as all the satellite infrastructure that really makes modern life possible. You know, when you actually stop and think about how much of life is dependent on things that we have in orbit, this very fragile ecosystem of communication satellites, GPS, weather satellites, you know, it's all far away, very difficult, very expensive, and at risk of collision. And, you know, before we can do anything like legislate space or figure out how to share it more equitably, or even just go and clean it up, we have to know where everything is. And we do a terrible job of tracking it. And that's actually where neuromorphic cameras can help. And the reason is that the way they work actually lends itself better to tracking objects in space that are moving than conventional cameras. So I like to show the slide. This is actually the telescopes we started with when we put neuromorphic cameras on telescopes. This was about 5 or 6 years ago now. And the real reason I want to show it to you is that we're still not using sensors that were built specifically for space imaging. And we're going up against astronomy cameras that are really the pinnacle of optical engineering in some cases. And they're actively cooled, very expensive, very highly, you know, refined pieces of electronics. And when you look at telescopes like this, the most important part really is not the actual telescope tube itself, it's the mount that you use to move it. And they're all built around conventional ways of doing astronomy. And what we're finding is by changing the sensor and changing the way you use the sensor, you need different types of hardware. And we're actually going to now start building our own telescope mounts because we can't get this hardware to do what we want to do with it. So I'm going to show you this little video here, which is the first event-based neuromorphic recording that we took through a telescope. That's Mars. And this was 5 or 6 years ago. So we've gone a little bit further from there. This is where we are now by comparison. This is a star cluster called 47 UC. As you can see, we can see a whole lot more stars these days. And what's really interesting, however, is what happens when you move the telescope. So if I went and tapped it, for example, in this case we're moving electronically, but what you'll see when I move the telescope, I don't get motion blurring like you would have in a frame-based image here. You'll see it here. I see the movement, but in fact, a whole bunch more stars pop out when I move. And that's really interesting because we actually see better when you're moving. So we break all the rules of conventional astronomy, right? And as a result of that, we can do things you can't do with normal cameras, and it enables ways of operating that people in astronomy just would never consider. And it's really culminated in these two shipping containers you see here. These are our Astroside mobile neuromorphic telescope observatories. So they're a full telescope observatory built into a shipping container. And the reason we can do this is because, unlike telescope observatories, we're probably the only people who don't mind a bit of motion. We don't have to sink concrete and stabilize our telescopes. We can have a little bit of vibration because there's a road nearby. And as a result of that, we can build them into a shipping container, which can go in a truck, a train, a ship, whatever you want, put it down, literally just plug in power, roof slides off, telescope comes up, it calibrates, and it can start imaging. It doesn't have to worry about where it is or how stable it is. And really, by just changing the sensor at the back of the camera, you go from a static building to something that's far more dynamic, and we can show the capabilities on top of that with these sensors that I'm going to show you some examples of that in a moment, that simply normal astronomy cameras just can't even tackle. And it's really all about doing things like this, tracking low Earth orbit satellites. This is a conventional frame-based imager. It gives you a picture every 4 seconds. And we're really interested in that bright object you see on the left there. That's the satellite. By comparison, if we track with an event-based camera or neuromorphic camera, you actually can see it continuously. So here's a similar object being tracked. You can see it's that dot there, but we can do things like move the telescope as we're imaging, and that gives us a whole bunch of power. You'll see the stars streaking through as we're following it, but we can actually tell a whole lot more because you're looking at a frame-based output of this. So we're moving the telescope around, almost drawing like an etch-a-sketch here. But in reality, that's a stream of events, and we can actually start even characterizing the object based on the information we're getting out of it. So in a second, I'm going to show you something that no one else has ever seen, because I only made it today. But on the 26th of May in Australia, there was a full lunar eclipse, and we were watching with one of our Astroside containers, and this is the recording. I apologize that it jumps around a bit. It's just got to do with the fact that the moon is larger than our field of view, and as a result, it's actually quite hard to track it without having to manually move it to keep the actual line that you can see forming across the bottom right there. That is the eclipse moving across the surface of the moon. And what's particularly interesting is you can see the line of the eclipse, but notice how you can see the part of the moon in eclipse just as well as you can see the top left part, which is not in eclipse. That's fully illuminated by the sun. So it's a really interesting, quite a nice demonstration of the high dynamic range and the importance of the independent pixels in neuromorphic cameras when it comes to doing satellite imaging. So yeah, this is, no one else actually has seen this recording, so something just interesting to show you. But now I'm going to pivot completely to robotic pinball, robotic foosball. Why we're really doing that, which is that one of the things I think we struggle as a field is conveying the benefits of our systems. And we certainly struggle with astronomy, for example, because all the metrics are based on frame-based imaging. And it's really hard sometimes to convey why your system doesn't do well on those metrics, but it's because they don't really examine the aspects of your system that you are exploiting or that you're highlighting with the way the neuromorphic approach works. And I think by building benchmark problems, challenge problems that take a specific task, or defined task or application, if you will, and then uses that to demonstrate some way of ranking objectively performance of different systems. So we started off by building a robotic foosball table. And I guess that came about from looking at how we've gotten to where we are with data. And I'd just like to go through the quick sort of history of that, which is really like, it all started with something like MNIST, which is a great data set because it's easy to understand, it's simple, it's like your sanity check for any deep learning system. Everyone needs a data set like that you run through, which is why it was logical that we created a neuromorphic version of that. But keep in mind, it inherits the frame-based nature from which MNIST was created. It's not native to how we may want to use these cameras. And sure, we've tried things like in our lab, for example, we use an e-ink paper screen to convert data sets now, and that lets us do things like very light level. It's still a bit of a almost ham-fisted way of doing it. And then some of the other things we've done is create a data set specifically to address where frame-based cameras have troubles, so high-speed ones, like where you drop planes in front of a freehand in front of the camera, where there's time and speed involved. And those get better, but ultimately you want a real-world problem. So we start with foosball. I just like this as an example because this is a valid shot in foosball, and it's so fast. If you look at the 30 frames per second out of a camera pointed at that, and if you look at the last 3 panels at the bottom right there, you'll see that the ball's only in the frame for 1 frame. So you either have to go fast and generate more data, or you can't do it with frame-based cameras. So with event-based cameras, it should be an easy task tracking the ball, but you have to deal with all the real-world aspects around it. So once you have it in a real-world task, it's much harder than you'd expect because of things like this. This is actually some real data, and on the right-hand side you see 5 sort of sections I pulled out. Now what's interesting there is of those 5, only 2 are actually the ball. The top 3 are actually the players. So simple things like pattern matching just don't work on this data very well. And I think that's something interesting. So when you check it from an abstract problem tracking a ball, which is easy with neuromorphic cameras, to a real-world problem, it becomes far more challenging. And also, some interesting research shows that the way we predict the ball motion and what you'd expect, it doesn't actually happen on the table. The ball moves in stranger ways than you might expect. So just quickly to finish up, I'll just talk about robotic pinball. And essentially, we thought about foosball for a long time. We thought, how do you essentially figure out if you're playing foosball well? I mean, we can sort of subjectively tell, but objectively it's hard. So we moved to this robotic pinball machine, which is great because pinball has a score, and a score is an objective way of saying if you do better at pinball in terms of score, you're better playing pinball. And the great thing about pinball as well, it's a really simple game. You've got 2 buttons, and that's it really. It's all about timing. And that's the real key here, because you can't cheat. If your algorithm is fast enough, you lose and you don't get a good score. So it's an unforgiving application in that regard, and it's a really good way to develop algorithms and compare and contrast them, because you have this absolute measure as a way of comparing them. So I think that's quite a quick summary, but thank you so much, and yeah, I'm happy to take questions during the panel session.
Thanks, Greg, and all the credit to you. You really have introduced the most cool applications for DVS. For those who don't know, I mean, Greg really started the whole space research. I think you mentioned that you met an agent from the Australian agency at a plane, at the airport, and that's where it went on. And I'm also have witnessed the excitement going on around the foosball in Telluride. It was definitely the most exciting project, drawing in almost everybody. Okay, but now we are moving on to signal processing. So Rob Mahony is on from the Australian National University.
Yes, can you hear me? Yes, good. So it's, as Greg said, it's after midnight here, and in Canberra it's actually 5 degrees. So many of you are sweltering away. Well, it's nice and wintry here, nearly the winter solstice. I want to talk about fusing some frame and event data, and so I guess I'm coming from a very much an engineering point of view, not philosophical about event cameras for their particular change the world point of view, but looking at event cameras and frame cameras together from a robotics point of view, they're incredibly synergistic. So event cameras are asynchronous, frame cameras are synchronous, event cameras are temporally dense information, frame cameras are spatially dense information. Event cameras don't get image blur, frame cameras you have an adjustable exposure to be able to get absolute intensities at different levels. Event cameras don't image static scenes, whereas frame cameras do. Event cameras have high dynamic range where frame cameras don't. So the 2 sensor modalities from a robotics perspective are incredibly synergistic. And if you can fuse event and frame data, you should be able to have it all. And so, images that are spatially and temporally dense. Now, obviously, you don't want temporally dense images all the time, but every now and then you do want temporally dense images, and you do want information in places. So it is nice to be able to get that. You want the high dynamic range, and you want to be able to image both static scenes and highly dynamic scenes. And so there's all these applications in event cameras for phones, augmenting existing imaging systems for all sorts of applications that are along these lines. So it's a very exciting question. So this is some of the work we've done, and the DSEC dataset came out just recently. And so I'll just show you some of the results that we're getting with the algorithms. I won't have time to go through all of the details, but the DSEC is great for us because it's a stereo event camera data set, but we actually don't care about the stereo that is being used in DSEC. What we're doing is we're taking the RGB camera and the event camera, which are effectively co-located, and registering the 2 cameras together, and then asking the question, well, how well can we reconstruct the actual scene Am I still
Lost your
going?
sound.
No, I'm not connected. All right, I'll just change. Where's my camera? Ah, this was bloody hell. No, this is not going well. Let's turn it. Okay. So microphone, that should be right. Speakers, you should be USB audio. I can't hear anybody. That's okay.
Robert,
Oh, we
can
hear
hear
you.
you. We can hear you. Robert.
1, 2, 3. Okay, I should be there. All right. Sorry about that, everyone. My headphones just died. All right. So we're in this situation where we can combine these two events, and as you can see here, the raw frame data from the camera is washed out, so it's overexposed in parts of the image, and in fact, in other ones, you'll see that you get blur. And the algorithms that we're using now with this data set are able to really reconstruct quite realistically the texture that's there in the roads, pull out texture in the backgrounds and in the image, which simply isn't there in the original image. And comparing to some of the state-of-the-art event-only constructions, you can see here with the E2Vid, there's a couple of problems that event-only reconstruction always has. One of them is getting absolute intensity information, and the other one is...
You're not sharing your screen anymore.
I'm not sharing the screen anymore, sorry. Am I sharing my screen now? Yep.
Yes.
Sorry about that. My partner is trying to sleep, of course, so I was trying to use my headphones, but then they died. So, all right. So I'll jump on to the next example just to show you that. So again, another data set from there, and here you can see one of the problems with learning algorithms. So, you know, we're not being fair to E2Vid here. We're simply applying it to the raw data, but it's not particularly well trained for the DSEC data, and so it's just simply going to fail. And that's one of the problems with learning algorithms, is that they're just not, there's always a situation where they're just not trained for the next set of data. Similarly, the ECNN algorithm that we were running down here is doing a better job because it's trained on a wider set of data, but still not reconstructing. You can see that the filtering that we're doing is doing a pretty good job. So we're very happy with the results we're getting. And this is a poor example of what we're trying to say here, but this is the temporal reconstruction. So what we're doing here is we're reconstructing a frame exactly halfway between two frames. So in the top left here, we can see there's 2 frames of data from this old data set taken with the Davis with significant displacement in pixels. And what we can see here in the reconstruction at an intermediate frame is we're doing a pretty good job of reconstructing. Even though we're using quite a lot of frame data in there, we're actually being able to cancel out the frame data. In this one over here, you can see particularly here, just on that edge there, you can see the previous frame as a sort of a shadow in the image. And that's a very common thing in trying to reconstruct temporal data and use frame data. So I'm, because of my problem, I'm a bit low on time. So I'll do 2 slides and then I'll jump pretty much straight to the end. So we all know, I think, about events and what they are, and the fact that effectively what you're doing is quantizing in intensity, but taking real temporal information out of the event at a level. And so what really the underlying principles that we're doing is to treat that then as a continuous time signal. It's not a continuous signal because it's quantized in intensity, but it's continuous time. And of course, if you just take that signal and you do a real integral, a temporal integral of a signal where these deltas are Dirac delta functions, it's the same thing as the algebraic direct integration process that people do. And of course, that's a reconstruction methodology.
The advantage of taking this perspective is that it opens up the principles of systems theory. So linear systems theory as a way of analyzing event cameras. And all we've done here is taken this expression, which is the integral of the events, and I've taken the Laplace transform. This really, truly is the Laplace transform of these signals, and you get exactly a transfer function representation of what to most people in event cameras is simply an algebraic summing process, but it actually has this linear systems process. And so direct integration, as we know with existing cameras, is really noisy. What we can do is we can do things like say, okay, well, we'll clean up the noise just by putting a high-pass filter on. So I'm just going to do it from a systems theory point of view, stick a high-pass filter on it, and that'll clean away some of the temporal noise that's coming in the DC area. All right, so the other thing that we can do is we might say, okay, we're going to put a high-pass filter on, but I can actually change the way I realize things like filters. And so this is a feedback realization of the same filter. So the transfer function that I get is exactly what I wrote before, but the way I wire that inside my algorithm is different. I wire it with this feedback loop. Because I do that, I get this ordinary differential equation at the bottom here, which is sort of underlying a lot of the work I do. Another thing you can do there is you can take frame data now. Here I've got my frame data, and it's low frequency, low temporal frequency, but I can add it in because the way this feedback loop works, it's sensitive to low temporal frequency data here and sensitive to high temporal frequency data here. And this is the principles of the complementary filter, which I worked on a few years ago. And we get a trade-off between the two. And I'll jump over a couple of these slides just to get to the main point. So the main point here in what I'm actually doing today is in the complementary filter, the actual gain that you use in that filter, which essentially tells you how to trade off, is a constant gain, is an engineered gain. And the work I'm talking about today is really about how to tune that gain in a sophisticated way. And so what we've done is we've drawn on the language of linear systems and Kalman filters to do that. And this is actually the main slide. So this is the algorithm that we're proposing. This part of the algorithm here is just the complementary filter, right? It's exactly the same as the filter that's been published already a few years ago. And what we've added to it is a gain tuning algorithm based on a stochastic fusion principle implemented through this thing called the Kalman filter. We need models, sorry about that. We need models of the uncertainty in the events and the uncertainty in the frames. I don't have time to talk about it, but it's in my other talk. And then we do a couple of other things. So we do a little bit of cleaning up of the signal first to get a bit more temporal resolution. And the other thing we can do if we want to is spatial convolutions, which people have done. And so what we get out of this tuning is it actually actively adapts the gain. So where you've got these washed out areas in the scene, it's trusting the events very strongly. And if you look in detail at this area, you can see it's a bit of a chunky sort of event reconstruction, but it's doing a reasonably good job. But here where it actually gets actual camera data, so there's actually reasonable intensity, even though it's quite dark, there's actually reasonable information there. And in that area there, it's augmenting the camera data to give you this high dynamic range resolution. And so we're getting these really good quality high dynamic range reconstructions out of it. And this is a video from the DSEC where the left-hand column is the raw vision, the middle top is the E2VID, the top right is ECNN. Whoops, I have to run it again to make it run. And the bottom middle is complementary filter. The bottom right is the asynchronous Kalman filter. We'll put this online so people can have a look at it. But the asynchronous Kalman filter is doing an extremely good job. So I'll quickly conclude and then hand over, and sorry about going over time. So I very much agree with Benosman's first talk about exploiting the asynchronous nature of the sensor and the algorithm design. So everything I've done is really designed to be implemented asynchronously, although at the moment the hardware available very hard to do that. So, we're still in sort of a temporal, sort of a problem in implementation. I think there's a really interesting problem in using frame and event data together, and I think there's a lot of really important applications there. So we're working at the moment on this stereo hybrid event frame data. The other thing is everything I've talked about tonight is shallow. So I'm just talking about these engineering algorithms effectively. And the reason is this one here, that I think we're in a period, a halcyon period in terms of the event camera sensors. So the quality of the sensors are improving so much year by year that as researchers in this field, I think it is necessary to really look at the fundamentals of the algorithm, not simply to learn from data to do better, but actually how can we build engineering algorithms that will work for any system so that the manufacturers can essentially just roll algorithms in that just improve the performance of what they're rolling out. So sorry, I probably went a couple of minutes over there, Cornelia.
Okay, thank you. Thank you. I think our next speaker from iniVation is missing. Is there a replacement from the audience? Somebody, Toby, would you like to say something? Otherwise, we move on to the discussion. Okay, I assume not. There were some, Toby, yes?
No, it's okay. Go ahead.
Okay, so there was one technical discussion that I see in the chat pressing that hardware people got involved, and we need Ryad to clarify this. So basically, what are the readout methods that you have used that are better than arbitration?
So
what sensors were those?
So there is a new class of sensors that are scanned, but scanned at very high temporal resolution. It's I don't know if you call it the hack or something else, but it's super fast. It goes 6 kilohertz. And then when you do that, you see that the pixel timing, the surface of events or anything is really smooth and nice. You still have noise, but it's nice and smooth. And times are really there. Most of the complication when you want to do event per event, that's why people want to do batches of events or frames or whatever, is because times are very unreliable and you have to always regularize locally. So anything that can bring you perfect timing is good. And there was also a skin, an artificial skin that came to Telluride a few years ago. It was no noise, it was beautiful. So I started putting all the algorithm and then I removed all the regularization for time because times were beautiful and everything could work. So I think the future is very close to what Cohen is gonna talk about today, which is this very nice 3D arbiter. But between the old arbiter that he has done, that everybody's using and not challenging since 2001, there is a long way to go. I think he brought it back thanks to this fence program and his other things. He must be around, right? And
yeah, I'm here. I'm here.
There he is. That's the guilty guy who brought that arbiter. No, I'm joking.
Yeah, it's not to that. It's not. Anyway, I put some clarification in the chat, but I didn't know about this scanner. So if you're going to be going at 6 kilohertz, how big an imager can you read out at 6,000 frames per second? I mean, it's not going to scale, right?
No, but it's for a certain resolution, it does the job, and it's still okay. It's still better than the old arbiter, because the old arbiter would stick somewhere, and then you times here, and then you jump, and then you stay there, and you don't know. Times are completely scrambled.
That's the 2000 arbiter. The 2004 arbiter doesn't do that, and this is what Prophecy is using. So it does it's a fair arbiter.
All of them. Yeah, I know Prophecy has improved it lately, but it's still based on your hack.
They're using the same design from 2004, which
everybody.
2000, yeah. But Ryad, let me just say, I'll get into this in my talk.
I know.
The reason why is very subtle, right? A lot of people are confused about this. So I'll try and sort of, if you watch my talk, I spend a lot of time on what's really limiting us. But ultimately, what's limiting us is that we have to put all this circuitry on the periphery of the chip. And then we have to drag these huge row and column lines. And it's just like So we have to do all these hacks just to squeeze performance out of it. But, there has to be a whole new approach, which I'll talk about.
Yeah, so just to tell you, the first stereo work we've done a long time ago, like around 2010, I had 2 cameras and I tried to match on timing, which looks really great if the arbiter was doing a decent job. And then you would see that some pixel arrived here and some arrived here, and then suddenly they never happen at the same time. That's why we had to regularize. And that's the biggest problem. I think that's why people are sticking to frames more. But it would, I mean, this is a beginning. So yeah, that's what I wanted to say.
Okay, thank you. So we're looking forward to Kwabena's talk later.
It's already online. You can watch it.
Okay. Here a few questions. Okay. As Ryad pointed out, the DVS concept grew out of biological considerations. Most work here on event-based processing has been technical. So where do you see opportunities for convergence research that ideally is bidirectional from science to computer vision, robotics, engineering, and vice versa?
I mean, all of us, I mean, for those who are computer vision, I see Costas here, and we've been around for quite a while, you also, Cornelia, and I think we've done the best we could with what we could with images and everything. And it's still engineering. Here, as I showed, we have a way to, neuroscience is there, and it's using the same format as events, slightly more advanced, more new things to learn. But that's the guideline, that's the data. My lab records from eyes and brains, but I think it's quite an oddity because, you record from things. If you get closer to neuroscience, you'll have lots of ideas because there is time. It's much more complicated than what we're doing, but there are answers there. I think all of us in the neuromorphic community, say Kobena, Ralph, every one of us know about neuroscience deeply to some degrees of knowledge. So what would you do if we had the opportunity to go away from engineering, which we will always be, we have all the engineering tool, and just get closer to the truth, It's this is my thought. And I think, see, when I talk with Kobena, we have deep discussion about neuroscience, although both of us, do technical stuff in engineering, and it's the same with many people. So it's a unique chance for us. You see, it's a unique chance.
You see that your hope is that more neuroscience will make better technical approaches?
Yes, of course. I mean, yeah.
In the design or better designs, Kwabena?
I think you need 3D. We're suffering to build a 2D, to use 2D chips to build a 3D brain. And all
you need 3D chips.
All these problems go down to wiring. We just don't have enough wires. And ultimately, you have to fix that problem to get the kind of quality that the brain has in timing.
Coben, I think what Cornelia tells you is how much from neuroscience you pick for your everyday work.
Neuroscience is not relevant in 2D unless you can go to 3D. That's what I'm saying. If you put it simple.
But you do read neuroscience papers, right? As I know from you when you read.
I'm not mischaracterizing what you said. I do read all those things, but
I know.
The deeper I get into it, the more I understand what the problem is that we're trying to solve, which is very different from what I thought it was 2000.
Veamos cómo está la restricción igual, porque es muy brígido.
I think somebody's
your point is if we go to 3D, we will eventually have even better designs.
No, then the way the brain is working becomes more relevant to the solutions that we need. Do you see what I'm saying? All these problems we're talking about is because we have to multiplex because we don't have any wires. Like, a ganglion on the retina, it's got its dedicated highway all the way to cortex. Nobody messes with it. It's got it. It puts there's spike time in millisecond time scale that's carrying information. Nobody messes with it. Right? If we have to, share wires, it's tough.
Okay, so what you're saying is forget about the classic computation and move the memory next to the computer.
I'm not saying that. I'm saying you need wires. There's no substitute for just more wires. You can fake it, but then you see these problems that Ryad is talking about, You can't completely fake it, You're going to get busted. So that's what's happening.
So through wafer vias, down multiple layers of chips stacked on top of each other.
Exactly. And and we are starting to, anyway, I'll get into this, Maya. We're starting to do this now. Samsung imager, Prof imager, they are 3D. There's two wafers, right? And so that opens up whole new things which nobody has exploited yet, which I'm going to show you how you can exploit. But
nobody, are you sure about that?
They are still using these algorithms we designed in 2D when we didn't have the 3D. That's what I'm saying. So it opens up the design space, and we should really exploit that. That's where you can fix these problems or start to fix them.
I think Cohen is giving you the hardware side of it. From a computational point of view, you see a lot happening when you get the real data. This is what a biological retina, you put it on the dish, you shine a movie on it, you can get the spikes out, the events out. How does it work? It's the approachable part of the brain. That's why we call it. And you see a lot there. And you see a lot today because we've improved neuroscience tools. You have better recording systems. You see stuff. And that makes you wonder, which are events? And of course, you can go back to a frame, but it won't be optimal because that's not what the story is about. So yeah, from both sides, we need to get closer to neuroscience, just a bit, slowly, reading, looking.
For Rob, if you don't mind, now that you mention it. So in the DSEC dataset, Rob, I think you showed some sequences at night, and I think there's lots of burst noise from the lights, but I didn't see it in the videos. So how do you handle those? How does the filter handle those?
This is because the lights are actually flickering, right? So they're actually a flicker that's going on. So this is actually data that's been developed by my students. So I'd have to actually have a careful look at it. But I think what we've done is we've just had a bit of a look at which actually frames we're picking. So if you dig through the videos, you'll actually find that it does flicker a little bit in the actual reconstruction. So we've just chosen the reconstruction to blur that out so that you don't see the flicker in the lights. We actually have some other algorithms that we're working on with Davida from Prophecy for flicker removal as well. So, but that's a separate piece of work. Yeah.
Thanks.
Does that make sense? Great.
Thank you. So I will pose one more question. What have we been missing regarding the concept of computing in time? It could be, where do you see interesting applications that could profit from that temporal advantage? I think that's what it comes down. Ryad pointed it out.
I think, yeah, the game today, every time when I started my career, people would call us and say, can you solve this problem for us? Now I get the same phone calls, but people ask you, can you solve that problem for us for 1 milliwatt? They come with a power budget. It's the IoT, it's the 21st century. And we want to get rid of clouds and networks and have everything in one hand. This is our promise. This is where we should go, and this is where we should deliver, because we're low power and low latency. So those are the two words, low power, low latency. That's what the market wants. Anything you can do with consumer market in that field is going to make a change.
So low latency, okay, yeah. Application low latency. And I will to satisfy also our sponsors, whoever they are, ask one ethical question that was in the chat, especially for Rob. So now that you're fusing with images with DVS, where's the privacy? Where's the computing on the edge?
So where's the compute, or where's the ethics?
No, I mean that kind of look seems like going back to classic Internet of Things with everything in the cloud when we're going back to images. While one of the points was really keep it local, right? Edge computing.
Yeah, look, I think there were two things there. One is that I think if you have an event camera and it's a good quality event camera, then the image is there, right? There's no encoding that you can't reconstruct the image. So the privacy question that was on the web, I fully agree with. There was a comment there that if you've got a good event camera, then it's you need to treat that image with the same respect you would any image at all. The other question here is around, why are we looking at combining frames and events? And because I also agree with what Ryad's saying, is that I think there's a lot of benefits in just working with events, and particularly putting the compute onto the chip so that you get rid of transporting data, which is the really big power consumption, and you get rid of latency. So I agree with that, but I also see lots and lots of engineering applications in combining the two. I mean, that first slide I put up was just the synergy between traditional imaging and event imaging. So if you want to have an iPhone that can take a photograph of a motor car driving past, a meter away from you, or take a photograph in a disco and do this sort of stuff, people in iPhone companies and smartphone companies, they will be putting event cameras with standard cameras and using them to get really good quality imaging. And so that, I think, is a massive application domain that is of significant interest. And that's really, really what that talk from mine was about, very much from an engineering perspective of I see the application.
If I could just add something to that, because Rob's right, but I think I have the extreme of that, which is for the telescope work we do, we still use integrating cameras, because there are things you can do with integrating camera you simply can't do with an event-based camera. So they complement each other. And there are tasks where, we'll never get to the sensitivity of a 30-second integration with an event-based camera. It comes down to physics at the end of the day. So sometimes you do have to integrate. That you maybe, moving away from the biological inspiration, but if you want to do a task, the combination of the two unlocks things. So, for example, often whilst we're staring to do integration, we're using the event-based camera to catch other things moving through the field of view, and that information together gives us everything. Combining them is the trick.
Can I say something? I mean, when you look at the way the human brain works, the periphery of it, all sensors, is sub-millisecond precision. And the deeper you go with understanding, and it becomes slower and slower and slower. There are two parts of the brain, a fast one and slow one. So we're not denying the fact that frames are there somewhere. So you can call them in the very slow prefrontal cortex, because you see me, so you have a stable representation of things. And if you work on that very fast way, you see me, you see your mother, you see whatever, it's gonna flip. So you need stability, and that's where frames are. And I agree that there are some engineering problems, and we cannot, give back the past. But when you look at the data, at least for a lot of what we need to do, you don't need frames. Of course you need frames if you need stability, or if you do a deep layer, your last layer, even if you're doing time, your last layer must be slow, because you have to get some stability in your visual system. But I don't believe, apart from pure engineering problem, that anything apart from just showing an image is always be beaten by events. That's for sure. Yeah. So an interesting comment on that, I can sort of agree with you. In these filters that I'm working, these linear filters, there is an internal state in the filter, which is the image, right? Now I'm stabilizing that internal state with an external image input. That's what's grounding it. But equally well, you could have a prior in there, or you could have an AI system that's stabilizing with semantic information, and that's essentially what the brain does. So, I just think there's an aspect of processing here which is very temporal, where the events are very high temporal information, and then you can actually use linear systems theory to actually understand how the slow information operates, in a sense. Yeah, there are different timescales. I totally agree. Yeah. But I mean, just going from events to frames and doing whatever, I think it's useless. Personally, you'd better take a real camera or an HDR camera. Yeah, but the real camera doesn't work in a disco. This is the point, right? I mean, there are applications right now where you can't get a camera to do it, and by combining events you can. So it's super exciting, I don't disagree with the philosophy that you're coming, but there's some problems out there that are super exciting to combine the two.
There's an in between, guys, right? Which is what I liked about the ATIS sensor, right? Which is where the intensity image is actually triggered by the events, right? So you get this distributed image that is not frames, but it's actually a synchronous image of intensity. And so only places where there are particular interesting objects or moving objects and so on, those are the places where you would get the intensity parts. So you taking advantage of that also, I think, can have a lot of profound advantages, especially in the bandwidth and communication side of things.
So just to add, I think I've never seen another group than ours do that, but long time ago, we've worked as events exactly in this point of view. You have an image, suppose a beautiful gray level image, and you just have one gray level that has changed, just one. What are you going to do? Are you going to do another Fourier transform on just one event or whatever? And so we show there is a class of algorithm that can do it that way and keep the image stable, which is exactly going and not offending anything from the incremental approach, which is you're computing something, whatever it is, it has to be stable. And every event comes and add to it. So you have two processes, one fast one and one that stays. And I think that's the way to go. Unfortunately, there's only one artist, and I don't think the company is doing gray levels asynchronously anymore. So I think Shoshone has one coming. Yeah, no, they're not. It's not on. I mean, I haven't seen it, but.
Okay.
Okay, thank you.
Thank you.
I think we are also on time, and
I think Cornelia, we were lucky, and Kynan was able to join after he had an emergency, and he wanted to answer something, but I think
I'm sorry about that. Yeah, unfortunately, I had a bit of a family issue and only managed to jump in very late, so I apologize.
I think we are actually already on time. If you want to say just a few words about your video.
Okay. I think I won't bore you. I mean, I think I'll just make one comment about the this events versus frames thing. You know, there's the sort of the theoretical aspects, and then there's what the customers tell us, right? What they want, you know, what they tell us they want, which is not necessarily what we believe they should have, is they want perfect events with no noise, and they want perfect frames, and they want it from the same camera, right? And they don't care if we have all these beautiful theoretical frameworks. They just want beautiful engineering systems. You know, we of course can argue about whether that makes sense or not, but that's what they tell us, right? And so, yeah, the Atlas, I think, is a very interesting way, you know, let's call it a sort of a biologically inspired way of getting grade level information. We, of course, have the Davis, which is, you know, global shutter frames plus the events. I think the way to go, at least from the short to medium term customer point of view, is to basically try to give them what they want, right? Because that's what they understand. That's what they can work with right now. They're not going to throw away their whole ADAS pipeline just because we have some funky new technology, right? It's not going to happen. All the automotive guys, they tell us, yeah, we'll put it in our car as soon as you have multi-megapixel frames as good as the frames I have now. And so I think that's something which we have to work on, you know, satisfying what the market's really asking for. Okay, that's my 2 cents.
Art still allows us to do science, as Ryad pointed out. Okay, so thank you all the speakers, thanks the questioners, and we'll finish this first panel discussion and move on to the second one, session 2.